You're muted.
Yes. Uh, Guys, we don't have that many people, so feel free to unmute yourself and then just talk to me. If you have a question, also just talk to me, like in the classroom. And like a lot of you don't turn on the video, I can't see you, so it's like I might not notice if you are wiggling around or something. Um, anyway, so here we go. Only took us 20 minutes, but we sorted out technology. And we're going to talk about covering number estimates. And this is the second time, second part of this excursion into bounding covering numbers and figuring out various ways of doing that. So just to recall, we had discussed the last time some basic relationship between covering numbers. This is what we call the inside covering numbers and the packing numbers. And the basic relationship we discussed was that covering numbers are upper bounded by packing numbers, which are upper bounded by covering numbers that have the scale. And of course, the two covering numbers are sandwiched between each other. So the inside covering number, because it adds an extra restriction to the sets considered, is going to be a larger number in general. So the first result was just the sandwiching between packing and covering. And the second result was talking about that if you have a norm on a Euclidean space, then you can upper bound the packing number of the unit ball with respect to the norm by this quantity, which scales basically with radius over epsilon to the power of k. Okay, so that's what you should be remembering. And that was just coming from some volume considerations, and that this is the right order is shown because we can also lower bound, and we did that too, the covering numbers by essentially the same quantity. All right. So the next result was kind of a fancy result, but it's just a Lipschitz result. It says that if you have a weight space and then you have functions indexed by these weights, and these functions satisfy a certain Lipschitz property, such that if you're wiggling the weights, then the functions cannot wiggle too much. Then you can upper bound the covering number of the resulting function space by essentially the same quantity as what you had for the ball, except that you have to include this Lipschitz constant, this gamma p, which measures how much wiggling the parameters is going to wiggle, how much of the wiggling of the parameters is amplified by this map that maps the parameters to the functions. So it's like the amplification factor, the Lipschitz factor, that gets into the covering number upper bound. The larger this amplification is, the larger the growth of the covering number. But it's generally, this is a mild growth because in all our results, we are taking the logarithm of covering numbers. It's like a log dependency on the Lipschitz constant. That's what you should be remembering. And earlier, we also had some results that were connecting covering numbers and bracketing numbers. And then, like, we had covering numbers separate bounded by bracketing numbers. And then if you're considering an L infinity norm, then you have equality. And if you consider the Lipschitz case, and then you want to consider the L infinity covering numbers for the function space. So here this P is infinite. Then this gamma p was measuring this was the amplification factor of this function gamma, and you just have to take the infinity norms. That's the usual Lipschitz definition, by the way. It's the usual definition of Lipschitzness. And so that just repeats the same business with the Lipschitz constants for the L infinity case. In this case, you can, this inequality, this just becomes gamma g of w minus g of w prime. And okay, this was an LP norm here. This is an L infinity norm. This is upper bounded by some constant gamma infinity times the norm difference between like the distance between w and w prime in the norm that you have chosen. Okay. And here this gamma infinity is just this constant amplification factor, Lipschitz constant. All right. So today we're gonna, like this was in the past, and today we start with talking about this pet project of removing a logarithmic factor from our uniform deviation bounds. So the uniform deviation bounds that we have for VC classes. So VC class is a subset of the functions that are binary valued over some space Z. It's like concept class, and it's called a VC class if its VC dimension is finite. So if you have a VC class, then currently we have an upper bound of this form for uniform deviations, one-sided, two-sided, doesn't matter. So basically it scales with square root d log n, and there's this log n divided by n. And the point is that if you try to work out the lower bound, you will see that the log n is not in the lower bound. You might suspect that you should be able to remove the log n. How do you remove the log n? So this log n was coming from Sauer's lemma. And okay, these guys figured it out, long story short. And part of the story is that you get better covering number estimates than what you can get from Sauer's lemma. And the storyline for that is the following. There was this guy, David Hausler, back in the 90s, and he was an excellent learning theory researcher. He did a lot of good work, and one of his results shows that the packing number of a VC class with respect to the L1 metric, but empirical L1 metric, can be upper bounded by this quantity, 1 plus log d plus 1 plus d times log 2 e over epsilon. So you see that, okay, as opposed to in Sauer's lemma, there is no epsilon dependency. Sauer's lemma just gives you this. Here there is an epsilon dependency. Okay, so that's maybe something that came in, but there is no log n. So there is just like a log constant factor over there. So if you choose epsilon to be just 1 over n, then of course you didn't do anything. And usually that's the choice that we make. So alone this is not sufficient. So you have to do other things. So people kind of figured it out. And the thing that you have to do is that you choose actually not the L1, but the LP norm. And you choose the LP norm with p equals 2, and then you can introduce some technique, it's called chaining, that we're going to talk about next week. And then these two things together and the generalization of Hausler's result that says that the packing numbers of a VC class with respect to any LP norm can be upper bounded by this quantity, where the only difference to Hausler's result is that you have epsilon raised to the power of p. And this together with chaining is going to allow us to remove the log n. The pesky log n is going to be gone. And that's like a big win, like we close gap between lower and upper bounds. So proving this result, oops. Yeah, just a moment. So we're not going to prove this result. The book has some proof of a result that is slightly weaker than this, and that would not be enough to remove the log. But it kind of shows the ideas of the proof. But I didn't want to go through that because we have a lot to cover. Kushagra? I can't hear you. You can unmute you.
I was just saying, so using the, so you're saying that usually we take epsilon as 1 over n, but in this case we are just like trying to optimize the epsilon by
Oh, it's going to be more complicated. It's like the chaining is going to create a whole chain of epsilons, and that's how you get rid of it.
Okay.
Yeah. So wait for that. Yeah, it's not just like that. It's a little bit more complicated. But here, okay, so Hausler proves these, the proofs, the book proves something slightly weaker. And then, but if you have this result, then you can figure out very easily that the packing numbers are related this way. So that's like just a little bit of syncing between the metrics, the Avon and LP metrics, how they're related to each other. And also that you can go from the empirical metrics to just any metric, and that allows you to prove this result. So these two parts, you should be able to do it after some thinking, and the something close to this is proven in the book. It's also like just a page length proof. It's not that complicated. All right, but now I'm going to leave this to its own devices. So we're not going to talk about this removing the log project is over for now, and then we are going to return it next week. Okay, when we consider training. And okay, so what other project do we have here? So the next project or questions is that can we have combinatorial dimension for real valued function classes? We already talked about that. Real valued function classes come up all the time. Let's say you have regression, then it's not binary valued. And when we had the VC dimension, then we basically had covering numbers behaving like this, d times log n. That was Sauer's lemma. And now you might suspect that, okay, no, it's real valued, then maybe the epsilon is going to matter a little bit. So maybe you can have covering numbers for real valued function classes that scale like d times log n over epsilon, where d is what? Like it's a VC dimension, but a VC dimension of what? Or it's a combinatorial kind of quantity that you would assign to this function class. And the answer to that is this is the so-called VC subgraph dimension of the function set or the Pollard pseudo dimension. So these words are written here. So David Pollard is another excellent researcher. He did a lot on empirical process theory, this uniform deviations, and much more. He's an excellent probability theory person. So what's the idea here? So the idea is that you have your function g. Okay, so this is my function g. It happens to grow, but it doesn't matter. It's just a function. So it's over the domain z. So this is my domain. And so it's like it just adds one dimension. And view the function from above as like giving you a partitioning of the plane into the blue and the red regions. And that's like the binary thing. The red becomes label 1, the blue becomes label 0. So for binary valued classes, we had the concept of VC dimension. And maybe if you want to talk about real valued functions, maybe it makes sense just to view them in one higher dimension as creating this binary classification or binary valued functions. Okay? So formally, you can say that, okay, if you have a function g that maps z to the reals, then you can create the so-called subgraph of this function that maps pairs of in the domain, like I said, and a value in the output space. So it's like you would have, I don't know, here you have a z, here you have a t, and then it lands somewhere. Okay? If this lands below the value that the g takes on z, you return 1, you're in the red region. Otherwise, you return 0. Okay? That's the idea. You create these binary valued functions out of your functions. And now you can work with VC dimension. We don't know whether this is going to be useful or not, but we can definitely just think about this and try this. It turns out that this is actually useful. They are even more refined. There is some issues with this concept, but it's by and large, it's a good idea, and it's good enough for the purposes that I want to use it for today. So then what you can do is that you say that, okay, like let's define this dimension, the dimension of this real valued class as the VC dimension of the subgraph class assigned to G. So what's that? It's like you have this subgraph function that takes, functions mapping from Z to R, and it returns these type of functions, binary functions. You collect them for all the functions that you had, and that becomes this new set. So now this is in 0, 1 to the power of Z times R. So just the domain, the dimensionality of the domain changed by 1. You added an extra dimension in a way. Like Z didn't really have a dimension, but it's like you're just expanding the domain, make it this product set, and now you have binary valued functions. You can just ask, what's the dimension of this? What's the VC dimension? Whatever that gives you, you're going to say, oh, this is the dimension for my function class. And so this is called the polar pseudo dimension or the VC subgraph dimension. And there are little observations here that you can make, right? So for example, if we start with our friends, the linear maps, so you have a weight vector in the d-dimensional space. Your domain is the d-dimensional space, and you consider the linear functions with some weight. So that maps a point z to the inner product of z with this weight. So that's like, just the linear functions. And you can collect these into the linear function space. Then what is going to be the VC dimension or VC subgraph dimension of this space? So this is a real valued function class. Well, the claim is that it's going to be at most d plus 1. Okay, why is it? Well, it's just using the definition. So the VC subgraph dimension of this class is the VC dimension of subgraphifying all the linear functions. Okay. And now recall that we had something already that we know about this other function class. It's called the linear threshold class. In the linear threshold class for dimension d, you have x coming from d dimensions, and then you calculate the inner product with some weight, and then if the inner product is non-negative, you return a 1, otherwise you return a 0. And so here x is in Rd. And we already saw that the VC dimension of this linear threshold class is D. So that was some discussion that we had before. And now just observe that the subgraph class underlying this d-dimensional linear functions, these are these functions. These functions here, they are just like d plus 1 dimensional linear functions. Just like there is one special weight vector that weight component is restricted to take on the value of -1, cannot take on any other value. So it's a subclass of the linear thresholds of dimension d plus 1. We added this extra dimension. The t is like the extra dimension, right? So z was d-dimensional. Z and t together are d plus 1 dimensional. Okay? So there is a subset relationship, and it's true that if you have some class and you have a bigger class, then the VC dimension of the first class is less than equal to the VC dimension of the second class. Why? It's because of the definition of shattering. If something was shattered by the smaller class, it's definitely shattered by the bigger class. So the VC dimension is monotone for inclusion. So now put everything together, and you get that the since we know that the linear threshold class in dimension d plus 1 has a VC dimension of d plus 1. You chain everything together, so the VC dimension of this guy is equal to this, which is less than equal to this, which is d plus 1, and you got the result. Okay. Good. Happy? Questions? Good. All right. Okay. All right. So
why is the subgraph function like that for this class?
why did we do this? Well, because we are trying, like mathematicians, they have too much time on their hands. They're playing around. They just try this. I'm like, it feels okay. You try it. Like, we have no reason to believe that this is going to work. This is going to lead anywhere. But recall what we wanted. We want to have some kind of combinatorial dimension assigned to this real valued, the class of real valued functions, such that the covering numbers can be bounded by similarly what we would expect to see from Sauer's lemma. So this is where we want to get to. We want to get to covering number bounds for guys like this, and we are developing this tool of VC subgraph dimension to get there, because sometimes this is a useful tool. And in particular, it's a useful tool when you see things like this, like the linear class. If you see the linear class, then you know that, okay, its VC subgraph dimension is d plus 1. And so you could plug in d plus 1 here. If you had something like this, that the covering numbers are bounded by quantities like this, you would be done.
Yeah.
Then you would have a covering number bound for the linear class. And then you can have covering number bounds for other things. Okay? So we are just building these tools.
Why do we have this log 1 over epsilon factor? Because Sauer's
we
lemma...
we have no reason to believe that it should be there or shouldn't be there. It was not there before. Now it suddenly appears. Well, we will see that why it's coming from. It's gonna be there. All right. So little homework. So you might think that, okay, like, is this d plus 1 or is this d? Like, there is an extra dimension. So the VC dimension of the linear threshold class is definitely d plus 1. It's not less than d plus 1. So then what the heck is going on here? Now we have less than d plus 1. Should this be equality? I claim it shouldn't. The book doesn't claim that. So I sent an email to Chung. I think I do have a proof that the VC subgraph dimension of just for d equals 1 of this linear class is 1. Anyways, moving on. So there is this other little proposition. If you have a monotone function, let's say increasing or decreasing, then the VC subgraph dimension of applying the monotone function to some function class is less than equal to the VC dimension of the original class. It's like there is some contraction happening just because you apply some function. It's kind of like pulls things together. I mean, except that like it's an arbitrary, but it's a kind of an increasing thing. So it, okay, there is a little argument that you have to make here to prove this. I'm not going to go through it. Like I included it here. If we have time, we can come back to this, but this is one of the optional things. It's like, you just think about, okay, if I have some set of points, so what do you need to have to be able to show that some inequality like this holds? Well, if you can prove that anything that's shattered here is also shattered there, then you're done, right? Because this can shatter maybe bigger things, but anything that can be shattered here is shattered by that, then you have the relationship. Okay, and that's how you start. Like you say that, oh, like let's take something shattered by this, and let's see whether this guy is shattering, and then you just think a little bit about it. Okay. All right, so next part of the toolkit is finally getting to covering numbers. Well, actually first packing numbers. So you can take the packing number of, okay, now the class has to be bounded functions. And you take packing number with respect to LP metric. Then it turns out that that can be related to the packing number of the subgraph associated with your real valued functions. Okay. And you have to change the metric. Like the measure in the metric gets changed. How? It's going to be a product metric, a product measure. So we had a measure over Z, that was mu. And we have the uniform measure on the 0-1 interval. Okay. You take this product measure and you measure, like you consider the LP norm with respect to that product measure. And so once you have that inequality, then Hausler's result that I was highlighting at the beginning is going to imply this inequality here. So you have this log terms, but then after that you have d log. This is just e. That's just a constant. It's just a bit messy, but okay, let me fix it. This is just e divided by epsilon to the power of p. So that's that. And so that's if you consider LP metrics and with p less than equal to infinity and greater than equal to 1. And if you consider the L infinity and you restrict yourself to just empirical L infinity covering numbers, then you see the full glory. So you have d, you have n, and you have epsilon. Okay. All right. So how do we prove these? Well, it's kind of just nice observations about, you know, how these metrics relate to each other and some Jensen. We'll see whether we want to come back to this. Maybe the second part is actually more insightful. So in the first one, you also see that the 1 over epsilon comes in. But it comes in because of Hausler's result. So in Hausler's result, we were trading off the log n term with a 1 over epsilon term. Okay, the same thing is happening here because the second inequality is just a Hausler's result, basically. And in the second result, you can directly see how this 1 over epsilon comes in. So we can try to do that. So we want to show that the empirical L infinity covering of G is upper bounded by some way. And the major assumption that we were making is that the VC subgraph dimension of this class is bounded. It's like a fixed number D. Okay. So we want to get this empirical covering bound for some sequence Z1 to Zn. Okay, and we know this. So let's shorthand like this SGG. It's like too much writing. I just write G plus. That's the subgraph class corresponding to G. Similarly, if you have a function and you want to take the subgraph function corresponding to that, you just write G plus instead of G. So this is these two notations. Okay. So Sauer's lemma. So this is Sauer. For epsilon smaller than 1 gives you that for any m, the uniform covering of G plus is just like a VC class. This dimension D is upper bounded by this quantity. So this is just like repeating what Sauer's lemma says. Okay, Sauer's lemma was exactly saying this. Like how fast the covering numbers grow as a function of the sample size m. Okay, and the conclusion was that the m appears here and like exactly in this form. Fine. There is no epsilon here. Okay. So far so good. So now, okay, questions. What is this? What is this m? What are we covering? What are we doing? So you fixed this point Z1 to Zn in the domain. So this is my domain. And let's say I have 3 points. And all the functions leave, like their range is the 0, 1 interval. So I'm going to discretize the 0, 1 interval. So I'm going to take this discretization points, epsilon, 2 epsilon, 3 epsilon, and so on and so forth. And I create this grid. So for every z and every point on my epsilon grid, I create a point. It's a pair. Okay? So this is going to be my S. So this is like these points are S. Okay? And U was just this set. Like this is like this. U has 3 elements in this case. It's like the grid on the y-axis. That's my U. So the coordinate of the U is at most 1 over epsilon. So I don't have too many points there. Altogether, the coordinate of this S set is like how many points we had here times how many points we have there, right? Okay. So now, because we know that, so what do we know? Okay, so we want to create a cover for G at these points, Z1n, Z1 to Zn. Okay. How do we create a cover? Well, we lift it to the subgraphs. We create a cover there for what points? For considering the subgraphs, their domain is the product of Z and the 0, 1 interval. So I'm going to propose that the points that we take is exactly the points on this grid. So the set S. Okay? So we are considering the set S. And let's get a cover of G. And so what does the cover do? Well, the cover, because this is L infinity and epsilon is smaller than 1, recall that the cover is actually what it has to reproduce the behavior at these points, at all the points that we are considering, at all the points in S, right? So if you take how the G plus, the subgraphs behave at these points S, then there are these functions, G1 to Gm. Actually, that shouldn't be M, like that should be capital M or something, because who knows how many they have, right? So they have, okay, maybe call it capital M, right? I'm going to call it capital. Because we know that in this cover, we can't have more than and here I have to write n times the coordinate of u, right? So we know that if we consider how many behaviors we get, we can only get this many behaviors. So there exist this many functions such that they produce all the behaviors. Okay, so these are my functions G1, Gn, but they're actually functions in G because every subgraph function is obtained by taking a function in G and subgraphifying it, right? Applying this subgraph transformation on it. Okay, so there exist G1, Gn, with n satisfying this inequality, that's I'm showing you here, such that all the behaviors at S are exposed by just considering these functions, G1 to Gn. Okay. So now we're going to claim that these functions, and there are capital N of them, are also an L infinity epsilon cover of G when restricted to the points Z1 to Zn. Okay. How do we do this? Yeah, let's take any element of G.
What is that 1 to n here?
1 to n.
Uh,
We started with this point.
okay.
So we are the uniform L infinity entropy for n points. This is what we are trying to upper bound here. N was the input. Like the bound that we are trying to prove has n in it. Yeah, we want to show that this guy doesn't grow too fast with n. So n was fixed. We fixed the points Z1, Zn. And now we are proving the upper bound just for Z1, Zn. You can take the supremum over the Z1, Zn, and you get the bound at the end. Okay? Yeah. Okay. All right. So we're claiming that these guys create an epsilon cover. And for this, okay, note the following. So you take any G, you want to see the behavior of G reproduced up to epsilon accuracy in the L infinity metric at these points. So G is kind of like, like an arbitrary function here. And you had some functions in your cover. I don't know, like they were going, who knows how, right? So what do we know? Well, we know that if we are considering the points of this grid and the subgraphified version of G, the behavior of the subgraphified version of G is reproduced exactly by one of the functions amongst G1 and Gn. Okay, so take that function. So that's this. Okay, so we know this holds. So what does this mean? The behavior is reproduced if and only if for every J, like every point here and every point here, we get the same values for both functions. And these values are what? They're just the indicators that indicate whether G is above or below some value. Like that's the value that you're considering here. So for example, you fix some Z here, and this is your U. Then if you see that, okay, this says, well, I guess I have the figure here. So here's the U, like you're flipping it on the side, and you see that the indicator indicates that, okay, like you have 1, 1, 1, and then 0, 0. If you have 1, 1, 1, and then 0, 0, then that means that both GIZJ and GZJ are in between these two endpoints, U and U plus epsilon. They are at the most epsilon away from each other, and therefore it follows that GI evaluated at any point Zj has to be in the epsilon close to G when G is evaluated at Zj as well. Okay. All right, so that means what? That the behavior of G is reproduced up to an epsilon accuracy by G of I. Okay, then that means that we were right. This is an L infinity epsilon cover. So know that we know that this is an L infinity epsilon cover. Okay, then we see that the covering number for G must be less than the covering number that we get for G plus. And here, the number of elements on the grid is at most n times 1 over epsilon rounded up. Okay? And now you use Sauer's lemma, and then you get this inequality, and then you can take the log, and then that gives you the result. Okay?
Can I ask a question?
Yeah.
So we know that there is a GI such that the GIZJ is delta close to GZJ, but does it guarantee any point outside?
No, it says that the indicators are like the zeros and ones are going to match as a pattern.
I see.
That's what we know.
Uh-huh.
So, yeah.
But this is only for like points that were given, right? Only for Z1 to N.
Yeah. So yeah, like you take any of these Z points, and you get this big pattern of ones and then some zeros.
Mm-hmm.
And that pattern is going to be reproduced for all the Zs. So it's like for all the Zs, you get 1, 1, 0, let's say, and then 1, 0, 0, and then 1, 1, 0.
I see. Got
And
it.
then you will have some function that reproduces that pattern. You take that.
I see.
And then you're arguing that for any of these Zs, they are epsilon close to each other.
Mm-hmm. Okay.
Which is,
Thank you.
Okay.
Yeah, it makes sense.
Yeah, okay.
Question: how do you know the number that covers all of your behaviors is a finite number? Like big N is finite.
Ooh, like for the binary case, it's definitely at most 2 to the n, right? And we were just using that. Actually, Sauer's lemma gives us an even better bond. Binary case, you can't have too many behaviors.
Mm-hmm.
So that's how we're building up things, right? Like the binary, sure, like that's just combinatorics.
Mm-hmm.
And then no real value, that's kind of like, right, but the discretization kind of saves us.
I see. Okay.
Larissa?
Yeah, I think The capital N should be at most 1 over epsilon to the small n, right?
No.
So
That would be
because
bad. That would be
yeah,
bad. The capital N is at most the L infinity covering number of the G plus class. That's a commutative thing. It's a binary value. G plus is subgraph.
yeah, I mean, in this case, we are using some additional assumptions over the G that, for example, we have the
Only
VC dimension
assumption
over.
that we use is that the VC dimension of G plus is D.
Yeah. So instead
Okay.
of 1 over epsilon to the n, we have 1 over epsilon something like 1
There's
over
no
epsilon
other
to the
epsilon
d.
to the N here. What? That would be
Yeah,
very
yeah.
bad.
Yeah, instead of that, we have 1 over epsilon to the d, for example, right? Because I think the bound that we have
We
is
don't have any epsilon dependency here. We don't have epsilon dependency. Right?
how? Because epsilon
This is what
d?
we had. Yeah. It was the
Oh,
VC dimension magic. No epsilon. Yeah. We are bringing that back in so that we don't have a lot of epsilon dependencies here.
right. Okay, yeah, that's really magic. So we should
Okay.
think more.
All right. Okay.
So just to reiterate what you were saying, so the point of using the subgraph was so that we can come to the combinatorial space and get the final result using Sauer's lemma, right?
Yeah. Right. Okay. All right. All right. So the next piece of the puzzle, and it's, trust me, there is some good outcome to all of this. Is considering convex Haas, and then this is where it gets interesting. Like we want to consider this infinite width neural networks. And so what was that class? So the whole thing is built up kind of backwards. Maybe I should tell you what we are shooting for at the end. So we're shooting for this little thing that you can call a corollary, but that's like, it depends on everything that was done before. Okay. So what does this say? It says that take a neural network, it takes inputs in d-dimensional space. So this is the input. This is in RD. Okay. You have one hidden layer. In the hidden layer, you can have infinitely many neurons. We're mathematicians, we are not worried about space and computers or something like that. This is for mundane folks. Infinitely many neurons, but so you have all these weights, not restricted. Here the transfer function is just the standard sigmoid function in the hidden layer. And then the output weights are restricted because we want to control capacity in some way. And they are restricted in such a way that their one norm is upper bounded by 1. So their absolute value sums to 1. Okay. And so if you're considering this, so this gives you this class. Okay, if you want to formally write it, H is the transfer function. You take, inputs and like multiply and then transfer, and then however many neurons you would have, arbitrary number. You just sum them up, weighted by these weights, and the alpha norm of these weights is bounded by A. Then we want to claim, and okay, so the A dependence should be there somewhere, but the main point is that this feels like a big class. I mean, like you have infinitely many neurons potentially, like there is no upper bound on the number of neurons here. You could literally allow infinitely many. It wouldn't make a difference, I think. But okay, let's say it's finite but unbounded. And if you consider the metric entropy with respect to the L2 metric, it behaves like 1 over epsilon to the power of something slightly less than 2. Okay? And as the dimension gets large, then it's just close to 2. So these classes, when you have 1 over epsilon squared, they are like big classes of functions, but not super big. The super big ones start when this power is higher than 2. So it's kind of like just like a very curious thing. And we are working ourselves towards understanding how you can come up with a result like this. Okay, this is more like an example in that sense that it's kind of just a very curious set of functions, right? And that if you consider metric entropy here, this is how it behaves. And also, if you want to, so the rates that you can get for classes like this is like, instead of the usual 1 over root n, that's not available because it's still a big class. You can get 1 over n to the 1/4. And that you get by trying to balance an expression like here this 1 over epsilon squared is coming from here. And 1 over n. So if you calculate what epsilon optimizes this, then you will get a rate like that. So it's kind of, yeah, this is what we are working towards. And how far did we get? So far, we were talking about these guys. So those are the linear guys. Okay, how their metric entropy behaves. Or if they are transformed by a monotonous transformation, that doesn't increase the VC subgraph dimension. So the VC subgraph dimension of these guys is at most d plus 1. And then the result that we were just considering, okay, the part that we didn't consider, that was the LP part. That shows you that the metric entropy of this class here, the F class, is upper bounded by 1 over epsilon to the power of d plus 1. Oh, that's not the metric entropy, that's the covering number with respect to the R2. And now what we want to do is that we want to convexify this. So the difference between the F class and the H class is that you're summing up the functions in the F class with weights that sum to 1. So notice that I included positive and negative sigmoids both, so that I can say that the weights are non-negative and that they sum to 1. I can take the positive parts, like if when you're summing up here, then you can take the positive part and the negative part of the real number, and then the real number is equal to the positive part minus the negative part, okay? So the negative part is going to correspond to when you take the H with a negative sign. And so all the weights are non-negative, they sum to 1. So that's like the convex class corresponding to F. Okay, so now we want to understand how that behaves if we understand how F behaves. So F behaves like how? It's, so this is the behavior of F. Like, how big is this class? It's like we have upper bound on the covering numbers, so that kind of tells you how big this is. And it scales like the linear stuff. It's like 1 over epsilon to the power of whatever the dimension was. Okay, so those classes are called parametric classes. So if you have such a parametric class, you take the convex hull of that. The question is, how much can you blow up the covering number? And then, okay, so there are these results. And actually, okay, so the result, end result is something like this. So you have a function class called f, and it's called a VCH class because everything has to have a name. If the metric entropy scales like this, which is exactly the scaling that we had here. It's just taking logs, like you take a log, then this d comes down, and then this log c over epsilon. So what do we have here? It's like the log guy is some dimension-like quantity times log c over epsilon. Okay, so if you have a class like that, then it's called VCH class. And that's sort of like a parametric class. Because after you take the log, the metric entropy depends logarithmically on 1 over epsilon, not polynomially on 1 over epsilon. That's the distinction between parametric classes for which you're going to get better rates and non-parametric classes for which you get worse rates. Okay.
So parametric classes have log 1 over epsilon.
Yeah, that's what people normally call log of 1. Yeah, like you call it parametric if it's log 1 over epsilon. People are not too precise with this terminology. It's like not too important to be precise about it because like you exactly calculate things, and then sometimes it's log squared and like, does it matter? No, it doesn't matter. Like there are functions between, 1 over epsilon and log 1 over epsilon. Where are you landing exactly? It's like, it's a one-off, but like by and large, that's kind of the distinction. Like 1 over epsilon, that's called non-parametrics. Log 1 over epsilon, that's called parametrics. Okay. In this part, so these are the people who are doing empirical processes. So this is their terminology for parametric and non-parametric learning when they are considering these function classes. Okay, and then after some work, you can arrive at a theorem like this. So if you have a VCH class, F, and you take the convex hull of the VCH class, then what happens is that you take the dimension, you multiply it by 2, and then divide by dimension plus 2. So I call V the dimension. And that goes into the exponent, but the whole thing becomes non-parametric. It's like there is a blow up because you convexify the class. But is it a very bad blow up? It's not a very bad blow up because here the exponent is still less than 2. So these are relatively small classes for which you can get okay rates. Okay. And then, okay, so if you take this result of van der Waals-Wanner, which is not proven in the book, but the book proves a series of results that lead to some result which is slightly worse. It's like this, I think. Yeah. And then there is some extra log terms which are not present here. So the difference between what is proven in the book and what exists as state of the art and tight results is that this log is not there. But that's much more work. And we don't even have time to consider what's done in the book. So I included some proof, but I'm not sure. It's like kind of, yeah. Anyway, so here this is just a constant that just depends on C and V. And so you plug this in, and then this is where this comes from. That's it. All right. Okay, so first result, we got some covering number bounds for neural networks, unbounded number of neurons. And why is it interesting? It's because like a lot of times people are like, yeah, you should just count the number of parameters, and then like that kind of gives you the complexity, the dimensionality of this thing. It's like, yeah, okay, but like maybe you have no bound on the number of parameters, like kernel machines would also be like that. So that's one objection. And then are you toast? No. There are many ways that the capacity can be bounded, and if the capacity is not that big, then you can get uniform deviations going, and then you can have meaningful theory for whether you can generalize or not. All right. Okay. So one more case, which is a little bit similar to the previous one, is norm constrained linear classes. So basically, you take a linear class, but it works with some feature extractor. So psi is extracting features from the domain. X doesn't have to be a Euclidean space; it's just whatever, graphs, whatnot, like molecules. It is. And then you take these linear functions. The weights come from W, and you allow the dimension to be infinite. So it's, again, like playing a little bit with that. And you're wondering about, okay, like how big is the metric entropy for something like this? And then you can have a bunch of results. So let me see. So, all right, so I need to tell you a few things about this. So we're considering the metric entropy with respect to L2 metric, and P is a measure over X. And this class is going to be just called the F class, and just abbreviate the metric entropy to an epsilon. And so you can take the sum of the squares of all the features. So the feature function psi has a bunch of dimensions. If D is finite, it just has finitely many dimensions, but it could have infinitely many dimensions. So what you do is that you sum up the squares of these functions, so pointwise squaring the functions, and then integrate them out. So if you take that, and that's bounded when you're summing from 1 to infinity, then this is a nice class. Okay, so we will call it a nice class then. So we're considering these when the sum of the squared feature components is integrable. That's the condition. And in more details, you can consider things like, okay, if it's integrable, then okay, it's a summable thing. And if you have a summable series, then the tail has to go to 0. So if you're summing up from an index that starts higher, then you get smaller numbers, and these numbers are going to decay to 0 because the whole thing was summable, so it has to decay to 0. So this creates this sequence of numbers, B1 and B2 and blah, blah, blah. The most critical is that B1 is finite. The others can only decrease. And I go to 0. And then you can, okay, let's say you consider just a 2-ball. So it's like, this is the 2-ball with radius A. And then you can take the first index such that if you take this decaying sequence of numbers, the first index where A times this decaying sequence of numbers is smaller than epsilon. Since B goes to 0, such an index exists, it's finite. You take that. And that you call the effective dimension at scale epsilon. And then you can show that the metric entropy at scale epsilon is effective dimension at scale epsilon over 2. So it's kind of like ballpark the same, times the log factor. So it's like these classes, even though there are infinitely many parameters in them, behave like finite classes, like finite dimensional classes, where the scale is going to determine the dimensionality of the class. And the proof is not too hard, but I don't have time for it. Some examples, if you take, for example, this B of J coefficients could be decaying like a polynomial, That's like a slow decay. Then you get a non-parametric class. Okay, and if the BFJs are decaying really fast, like exponentially fast, then you kind of get a parametric class. Okay. And Zhang has two more results that for the uniform metric entropy and these numbers are the same as before. So this is the radius of the ball in the weight space, and we just call B1 B is bound, and then you have this A times B over epsilon squared behavior. So that's like the non-parametric case or non-parametric style behavior, and then there is a log factor. And if you're switching to in the weight space, you allow alpha norm. So the alpha norm is larger than the R2 norm. Okay. But you take the dual of it, that's the L infinity norm for the feature space. Then you can bound the metric entropy almost the same as before, except that there is a dimension dependence now. So this doesn't allow infinite dimensional spaces. It's like it's tough. All right. Okay. I think that that's it for now. So I think that we saw at least one interesting case or a couple of interesting, maybe two interesting cases. These neural networks should be quite interesting. And then these linear classes are also quite interesting that you can allow infinite dimensional things and then things still work out, and it's kind of neat. All right, I'm going to share the notes and yeah, and we take it from there. Next week I meet you in person again. Okay.
I have a question.
Questions? Yeah.
So initially we were working with the L infinity norms, but then we suddenly switched to L2.
Yeah.
What's going
What's
on
the
with
deal? So if you recall, the results that we get for uniform deviations were for L1 actually. And if you consider all the LPs, the L infinity is the harshest. The L1 would be the nicest to work with, but you can rarely do that. So you kind of like try to navigate that space. So the L infinity was super easy and nice to work with. It was easy to create these covers. With the R2, we are struggling a little bit more, but it's going to lead to better results. That's the deal. That's the game that we are playing.
And L infinity is the hardest?
L infinity is the easiest to prove, but gives the worst results.
Yeah.
Like it's like all these metric entropies increase with P increasing in the LP norm. Yeah.
And then
So
also the when we had the results for these surrogate losses, we also had this like norm like quantities, and you were saying that sometimes even when like D is infinite, we can allow for like we can replace this with these A squared B squared over epsilon squared like quantities.
okay.
Is how is this related to that, or is there any relation?
I
Like
don't think it's related.
because in the final result there was some A squared B squared over epsilon squared for the metric entropy bound, like so the bound that you showed today.
Okay. Let me try to recall. Okay, found it. Oh, yeah. I mean, like, okay. Yeah, we were just talking about these results that I was presenting today at the very end. But we didn't prove anything with it. We were
Mhm.
just saying that, yeah, results like this are possible.
And
Yeah.
and then usually we have like square root of log of metric entropy. So I guess the final bound would be just a
No,
times.
the metric entropy already taking the log, so it
Yeah,
will be
yeah,
too good.
yeah.
So
But
either
then,
you say square root of log of covering number, or you say square root of metric entropy.
right, square root of metric entropy.
Yeah.
So the metric entropy is of the order of a squared b squared over epsilon squared.
Yeah.
And then,
Yeah.
uh,
Then you get this n to the 1/4 behavior.
uh-huh,
Yeah.
I see.
It's not that pleasant. Better than nothing.
Hmm.
Sometimes you can prove that this is tight.
For like these big function classes.
Yeah. Or if you consider surrogate losses, maybe in that case as well, because you kind of like just doing things a little slightly off. Okay. All right. Thanks. We'll take it from there. You should go climbing alone. I miss you. See you.
See you next week.